Hello, everyone. Thank you for coming to another IMB-CNM talk. Today we have Jofre Pallarès, who joined the IMB-CNM in 2002 to develop his final degree project, which he finished in 2003 to obtain the master's in electronic engineering from the UAB. As part of the ICAS group, he worked for 5 years as an analog designer for Epson Europe Electronics GmbH, and after a short experience in the private sector, working as a research manager for Control SA, in 2009, he rejoined the ICAS group to undertake design work and develop CAD tools for printed electronics. Since 2015, he is a member of the reverse engineering team, where he performs a wide variety of tasks, from sample preparation service for clean room process inspection to European project coordination. So thank you for coming. Thank you for joining us online. And Jofre, the floor is yours.
Okay, thank you, Isabella, for the presentation. Thank you, all of you, for your attendance, both here and virtually at home. So I will present this presentation titled Forensic Reverse Engineering of Silicon Chips, the ForRES project. But since this is a project that has not started yet, okay, I will try first to make a brief introduction on the reverse engineering task of the IMB-CNM, what we are doing on our team. And then I will present the X-Files project. It's a project that it's just finishing this month, but it's the parent of the ForRES project. Okay, so I cannot explain the first project without explaining the X-Files project. And later on, I will present just 3 slides about the project that we are going to start. Okay, so we are the reverse engineering team at the IMB-CNM. We started with the foundation of the institute as an internal service for the clean room process verification, also for fault analysis of the devices fabricated in the clean room. So we are officially scientific technical service of the clean room ICTS, okay? But we also provide services for external companies from the middle 90s. Our main activities are the sample preparation for microscopy, most of our internal service here at CNM. And also we develop analog and digital IC reverse engineering, which implies most of our research. Okay, this is for internal, but mainly for external companies. And just from this month, we have a new machine, a speeding resistant profiling machine, that is a new service for the scientific technical service of the clean room. But I will try to make another presentation another day about this machine. We are a 8-member team, a very reduced team, because only 2 of these people is in full-time, Roger, Dura, and me. Okay, most of the people are part-time, and I take this opportunity to present Nico and Danny there, that are the new members of the group from this spring. Nico is in a part-time contract, and Danny is developing his final project, TFG. Okay, so let's just talk briefly about the sample preparation for microscopy. That's the main service we provide to the institute. Okay, so what we do is prepare the samples for inspection. Inspection, for example, with optical microscopy or SEM microscopy, also for example, live decapsulation of devices for thermographies, and we have a wide variety of techniques like cross-sectioning, surface polishing, chemical attacks to expose the diffusions. For example, in this case, you can see here the diffusions clearly seen on this device. This is after a chemical attack and using polarizers. And we also make non-destructive decapsulation, okay, for testing. This is our main internal service, and our main external service is the analog and digital IC reverse engineering. Okay, most of our research effort is here. And we have more than 20 years experience on full IC digital and analog circuit extraction. Okay, it's a very complex process. It implies a lot of processes like chemical decapsulation, mechanical delayering of the chips, also reactive ion etching of some layers, wet etching of other layers, image acquisition using high-end machines like the Drive e-beam machine we have here. Okay, but also it implies a lot of software, dedicated software to manage all this data. And in this case, we have from more than 10 years ago, we started to develop our own software because there are very few commercial softwares that can do that and are not so well developed. So we will develop our own software that can stitch the images, send images, can navigate in these images, and also it can extract the features of the circuit. It can extract, well, probably it will be better if I show just a short video of our software. Okay, it has this same image of a layer of a circuit. Okay, we can, this is a single image, but we can stitch many images. This is not only stitching, okay, it's stitching, correcting the distortion of all the images because same image has distortion, so it's a complicated process. But we can also extract the features. So from a same image, okay, we can we have trained it with artificial intelligence methods. We have trained this program to identify the tracks, also to identify the bias, and also to identify the dust, because there's always dust from the process. So, for example, here you can see just a small part of a circuit. This is just a small part of a circuit, but there's a lot of data here, and you can see here all the tracks. But we also can change to another layer. So here is another layer of the same circuit. Okay, so this is just a small example, only 2 layers, a small part. But yeah, here you can see the features of another layer. You can see that the image is quite blurry, but with this artificial intelligence methods, we can extract the features quite easily. And also, for example, this program also incorporates other features like navigation, for example, from 2 layers at the same time. Okay, so we can put these 2 layers, but the cross is in the same point. Okay, and so we are in the same part of the circuit at the same time. So we can use these features, for example, to align properly, to track, to see where it's going the signal from this part to another part, etc., etc., etc. Okay, what we do with this software, well, the main idea of this software is once we have everything properly aligned or properly corrected, we can export this data to a GDS. Typical mask data, and using a commercial software like Cadence, for example. This is Cadence Virtuoso. We can navigate in the circuit, but we can extract all the circuits. So from here, we can detect the devices, we can detect all the interconnections, and we can get a netlist. Okay, so that is the reverse engineering of the complete cycle of the reverse engineering. Well, there's a final step, which is the knowing what is doing this netlist. This we explain it in another day. Okay, which are the applications of that? Applications, there are many applications, but we can be for fault analysis or security audits. Also, for example, for patent protection. Okay, we have many requests for legal questions, also for competitive analysis. Okay, but this is a very, as I said, very complex process. Okay, it implies a lot of expertise and very high-end machines. So the full analog and digital IC reverse engineering usually is limited to some big companies, okay, but also on national security agencies or law enforcement agencies. Okay? So they have big money. Okay? That means that there are very few papers on this field. So for us, very difficult to get information to stay in the state of the art. Okay, so our way to stay on the state of the art is to collaborate directly with for example, law enforcement agencies. So we have, for example, a direct collaboration with different policies. Law enforcement agencies from other countries, and with this collaboration, we have a regular meeting every year where we exchange all the techniques or all the findings or our experiences with the machines. So from these meetings, we try to go one step further, okay, and apply for a European project altogether. And this was the beginning of the X-Files project. It's a project we applied in 2018. Then we get rejected. We applied it again in 2019, and we get the project, and it's finishing just now. Okay. So this is the project, the X-Files project. Okay. Acronym is for extract forensic information for law enforcement agencies from encrypted smartphones. Okay, it's a security call. Okay, and we have 14 partners. 5 of them are law enforcement agencies. 4 are from the public research field, and there are also 4 cybersecurity companies and 1 for coordination. It's a 7 million project, 100% financing, and we get 400K around. Okay. And it's finishing just this month. Okay, which is the motivation of this project? So taking from the proposal, it's improve law enforcement agencies, techniques, and methods to extract digital evidence from modern encrypted smartphones. Why? Why? Because the data stored in mobile phones always contain critical evidence. It's the main source of evidence in criminal cases in the present days. Okay, but the latest generation of mobile phones usually incorporate memory encryption. That means that if we don't know the key, storage inside the mobile, if we don't know the key to encrypt this memory, we cannot access the data. It's a very, very big problem, because before that, the unencrypted phones were quite easy to open. It was a straightforward procedure, only 2 hours. It was very easy. Just open the phone and take the memory chip, or look at the memory chip with a laser, and remove the epoxy on the memory chip, and just bond some wires on the serial interface of the memory chip, and just download all the data. That was the usual procedure, and these law enforcement agencies were capable to do that in less than 2 hours in a very safe way. Now, with encrypted phones, it's not possible anymore, and we have to use another techniques. For example, the most usual one is the exploit of unintended software backdoors. Always there are some bugs on the chips, and this is the main approach to de-encrypt a phone. Also, there are some side channel attacks. For example, just trying to put a laser on the chip while it is working, and making some security steps, try to modify the logical state of some areas using lasers. Also doing the same with power glitches. So while it's booting the chip, you can apply some very dedicated power glitches just in the boot, for example, of the chip, and then you can bypass the security. But they are very, very, very complex. They are very, very complex techniques. And the problem is also all these techniques are dependent of each target. So for each chip, you have to develop a new technique. So, well, this is a very costly thing, and we try to overcome this by applying for this project. And we will try to use software, hardware, and software. Well, we are using hardware and software methods, or a combination of them, to try to de-encrypt these mobile phones. Which is our role? Well, for our background, we only participate in the work package 4, which is dedicated to hardware methods. Okay, and our main tasks are, among others, to work on the definition of the suitable delayering techniques for the system on chip. Also to process and extract non-volatile memories, such as ROM banks or fuse banks. why are important these memories? Because, for example, in a ROM bank, which is a mask-based data, like this one, okay, those are the actual bits of a ROM bank of a chip, not from the project. Well, it's important because this ROM bank contains the boot ROM, and getting the information of the boot ROM, you can pass this information to a guy that knows about software, and he can try to make some attacks based on this data. On, for example, the fuses, you can see here an image from the fuses. It's not from our project. Due to confidentiality issues, I put the images from the internet. Okay, so these fuses here, okay, are the typical fuses you can find in a chip, and the fuses are usually used to program for each chip a unique ID or an encryption key. Example. So getting the info from the fuses can give us a lot of information then to try to generate an attack. So we do all the process. So then we will make the encapsulation with the chips, the layering, the processing, the image acquisition, and then also the value extraction. So we extract the value of these fuses using these artificial intelligence techniques. Okay, because we have to do it because we cannot do it manually. There's a lot of data, usually thousands or millions of bits. So we have to do it in an automated and reliable process. Okay, just as a success story, there are many success stories on this project. I can say that we have done more than expected. Okay, but this is an example of a success story. So for one of the target phones, we developed a method to expose the fuse bank, okay, and get all its data. So it's more than 20,000 fuses. So we developed a way to safely get all the images of the fuses, extract all the values. Okay. Finally, after breaking more than 20 chips, we get a process that it's just 12 hours, and this 12 hours, it's 8 of them, it's only for imaging. So we can start processing here, left the chip, put the chip on the right 150 machine we have in the clean room, and left the machine making the images during all the night. And next day we can finish the process and get all the data from these fuses. Okay, the problem is that we don't know the organization of this memory, how is organizing the data. So with collaboration with the Dutch law enforcement agency, they programmed 4 different chips, 3 different chips. They programmed the chips with some fuses blown, with some pattern. Okay, we get these fuses. We get the chips, extracted the fuse values, sent it to them again, and they could then understand which was the memory organization. Okay, and they could locate an encryption key, the main encryption key. And this encryption key is used on the phone, is used to derive the memory encryption key. So then with this information and using brute force, just with some seconds, they can de-encrypt the memory. So it's a very success case. So now they have this technique for further use in criminal cases. Okay, so which were the main lessons we get from this project? First was in the proposal, because on the first proposal we get a 9.5, which is a very horrible punctuation in a H2020 project. But all these leaders were quite happy. They said, "Oh, it's a nice punctuation. Let's try to apply again." Okay, we apply it again, and we get then a 14.5, which is a very nice punctuation. Which were the changes? The changes were some cosmetic changes on the proposal, but we put more emphasis on legal and ethics, which is quite important for this kind of projects. Okay, and we improve it a lot. Also, the competence and the reviewers are not the same. So my advice is if you get a bad note on a project, don't put it on the desk. Try again. Just make the modifications that the reviewers are asking for and try to again. Okay, but the main lessons we get from this project is the confidentiality issues. Most of the partners were completely new in this kind of security projects, so we have no experience on that, and we made many mistakes. Most of them on confidentiality, because since there are many of the information in this project that is completely restricted or confidential or classified also. We had to make an example, a safe encryption and storage system for classified information, and it must be approved for the national security agencies of each country. So that implied that, for example, the first 2 months we could not change any information on the project. Also, we had to finally to put a dual space on the cloud to change the information, public space of when all the universities could access, and restricted space where all the people only the people who had access to classified information like us that could go there. We had to create a security screening board that approves every information that has to be published, has to be approved before for this security screening board. Also, we had a lot of difficulties to report the project developments to the reviewers. It was difficult because not all the reviewers could access to the restricted information, and it was quite difficult, because imagining a presentation with no images, just words. But we were quite happy. We got nice results, and we think that we thought that maybe it was better to apply again, continue this project, but more restricted to the reverse engineering part. Okay, so this is the beginning of the ForRES project. This project, as you can see here, is from the same. I just eliminated the partners from the last graph, so we are the same. The 3 years, the CNM and a private company, all of them were in the X-Files project. We are the only one research center, okay? And this project, well, this is the name, and it's in the Internal Security Fund of the European Commission. It's starting just the day after finishing the X-Files, which is quite nice. And in this case, we have asked for this 286K euro, which is the aim of this project. So this is also from the proposal. The main objective is to push the boundary of IC reverse engineering below the sub 28 nanometer node by improving the techniques for analysis of integrated circuits, or facilitating the European cooperation through the unified tool panel. A very long motivation. Just let me explain what it means in just going for the detailed technical work packages. So the project is dedicated to improving the reverse engineering capabilities of the law enforcement agencies. Okay, and we have 4 technical work packages. One dedicated to the sample operation, the layering and imaging of leading silicon devices. Another one is dedicated to the software, okay, so developing software for extracting the netlist or the ROM data. Another one for identifying and implement silicon edit on leading edge semiconductor devices. That means when we talk about editing silicon, that means focus ion beam. So it's techniques for focus ion beam to modify the circuit and, for example, overcome the security of the circuit using this kind of techniques. And finally, there's a work package dedicated only for to collect all this information and create a wiki, like a wiki of methods, targets, and so on. Okay? Which is our role in this project. Most important thing, we are the technical coordinators of the project. We're proud of that. And on the work packages, regarding the sample processing and imaging, Okay, I have to say that we can apport our experience, but we cannot do so much because we have no broad ion beam. Broad ion beam is a kind of machine that we think that is now the only current way to delayer the modern chips. Modern chips has, for example, the oxide interlayer is this less than 15 nanometers. Okay, so the layer this in a mechanical way or using the traditional mechanical ways it's almost impossible. So we need to go to specialized machines like this broad ion beam that can delayer in a very precise way. But we don't have this machine, so we can only apport all experience, for example, our method for initial planarization of chips, and then that's all from our side. But we also can help on imaging because we have a nice machine for imaging these chips. So we will participate only in this thing. Regarding the software, of course, we are the most experienced group on this part. We can apport our experience on the software development, and also we will be in charge of the non-volatile memory extraction, so the fuse and ROM extraction. And regarding the FIB, the FIB package, well, we will not work so much on that. Other groups are more interested. We are only can give advice and use our FIB as a backup in case of other FIBs broke. And the last work package, the library, we are the work package leaders. So we will create and maintain this library. And well, there are not so many lessons because it has not started yet. But as I can say is that we made a very rushed writing in August. Everyone was in vacations. It was very difficult to write the proposal. From my opinion, it was a quite bad proposal. I was going to vacations thinking that we will not get anything. But finally, we get the project. So again, you always have to know. Please present it. Probably the highest points of our proposal that we make a lot of importance on the cross-border collaboration between LIAs, and also that we say that we are saying that all these results will be public. We will share this software with other LIAs. We'll share our knowledge with other LIAs, of course, using some kind of agreements, but we will collaborate with other law enforcement agencies across Europe, and that's very important for the European Commission. Okay, and taking our experience from the last project, all the results will be public. There will be not target devices, so they will facilitate our work in this project. And I think that's all. Thanks for your attention. And if you have questions.
Thank you, Jofre. Any question?
David?
Yeah, you mentioned in the ForRES project that you want to about medical 28 nanometers.
Yeah.
Is there any reason why the 28 nanometers? Because the limit, no? You cannot be low.
Yeah, probably it's more for the background we have, because on the X-Files project, initially we said up to 28 nanometers. So then we are going a step further, but it's not true because in the X-Files project we will go below the 28 nanometers. Okay, but I can say that more or less modern chips are below that. I mean, yeah, there's still a lot of chips on 22 nanometers, modern chips. So that covers, yeah, well, we can say modern chips.
Luis?
Which is a different node that you have been able to go.
The lowest depends. For example, the lowest features. We have made some works on 14 nanometer. Okay, but yeah, we cannot make all the process. I mean, we are not capable now, right now, here at CNM, to make the layering of a chip below 65 nanometers, I think. But we can make some process or access some of the layers if the information is located on the lower ones or the upper ones, then yeah, we can go for example, for 14 nanometer chip. But just only in this case, the information is on the first metal, for example, or so on. I mean, for example, this ROM data, okay, usually it's bias, okay, it's the existence of or not of bias on the lower side, or for example, contact bias or metal 1 to metal 2 bias. So we can access to the chip from the backside of the chip, and just with some wet or dry etching methods, reach this layer. But we cannot use mechanical layering on that. I mean, if the information is, well, what I want to say, if the information is on the middle layers of the chip and between metal 5 and 4, then we have a problem. Okay.
You see that you will not use the ion beam etcher, the EIB.
Broad ion beam.
Yes, because you don't have it.
Yeah.
Yeah. Some other partner has this equipment.
Yes.
Yes. And you are planning to buy one.
We are dreaming of buying one, but it's 600-700K euro, and it's very difficult for us to try to get this machine from a project, because these machines are, for example, the delivery time is 14 months. So if we try to apply this machine inside the project, we will get the machine at the last year of the project. So it's
not for the project, but in the future of the laboratory.
I think it's a key for the all future. I think it's a key for
the size of the sample.
The sample size can vary between 1 square millimeter to 1 square centimeter, for example, or more, or 100 square millimeters. Sorry, it's the same. But yeah, these broad ion beam machines usually can cope with wide area. What I mean, for example, 4-inch wafer, they have, I think, less than 1 or 2% difference on etching for inch wafer, which is quite nice. Yes.
Another question: the chips that you are using, where?
Okay.
Where you went?
Yeah. So yeah, it's a very good question, because in this case, for this project, sorry, for this target, we could get the chips just by AliExpress, only 20 euro per chip. But in other cases, we had to buy phones on eBay. Broken phones, so I have a lot of broken phones at my laboratory.
But you don't need a special permission or something to analyze these chips.
No. Analyzing it's completely legal. It's legal. What is not legal is replicate a chip. But if I want, I can show this information and show my methods on a blog and so on. I mean, there's no problem, legal problems in that. The problem is try to replicate. I think that is patent protected. It's not patent protected. Yeah, and you can also replicate some of the parts. So yeah.
More questions?
Yeah. All the methods you have shown are destructive for the chip. Is there any method that you can use that doesn't makes the chip usable?
That's a very nice question. I will repeat it because we are quite far from that. I don't know where you're at home. He's asking if all the methods I'm using are destructible, or if there are some methods that I can apply that not destroy the chip. Okay, yes, that's the. In this case, the focus ion beam methods, it's for it's non-destructive method. The idea is for example, try to open a chip, just make a local opening with a focus ion beam and change, for example, one of the lines dedicated to say if it's protected or not. For example, if I have a line that his logical value then says if the chip is protected or not, if I connect this line with a focus ion beam to another part of the circuit, to ground or to power, then I can change the protection state of the circuit, for example. So we have a work package just dedicated for that, to try to make live editing of a chip without destroying the functionality.
But the reverse engineering of the whole chip, like, can you observe the whole chip without destroying it?
No, there are some works using very new X-ray machines. Also works with synchrotron light to try to do that, but very difficult. Just now it's only for a small part of the circuit. Please.
You said that you're using artificial intelligence software to speed up the process.
Yeah.
Which are the usual times involved?
Well, it's not only for speed.
The whole time to the features, but afterwards.
Yeah, it's. I mean, when it's speed up, it's to speed up and get a reliable info. Because, for example, on this kind of images, the ROM data, here you can see a differences on contrast on the SEM, because some of the parts are connected and some other parts are not connected. So you have a difference, and you can extract this just using brightness thresholds, for example. This was the traditional way. Okay, but for example, it's not a reliable way to do it. I mean, you get a lot of errors. And how do you? How are you sure that you are your data is correct? Because maybe if it's 1 megabyte of data, you cannot check manually 8 million samples. You can, for example, check which are the samples that are close to the threshold, for example, it's a way, okay? But you spend a lot of time doing that. With artificial intelligence, you still have to check for the bits that are around the threshold, but there's many times less errors, and most of the errors came from dust on the sample. So yeah, probably it was a great improvement to use. Oh no, not so much. I mean, minutes to do that. Maybe you spend more time trying to train the machine. Okay, but once you have the machine trained, we are doing that in a two-step. I mean, have some. It's a pre-training, and then for each target, special training. So this pre-training is quite complex, but then for each target, the training is also some minutes, not so long.